Welcome to the Royal Institution and to the unique atmosphere that pervades this place. This is the most famous theatre of science in Europe, housed within a large building in Mayfair that contains also the oldest continuously used scientific laboratory in the world. At this time of year, ever since 1826, the school children of London have crowded here to be entertained, to be educated, to be inspired by the foremost scientists of the age, who have been asked specifically to design special experiments and demonstrations that illustrate the progress in their subdisciplines, their excitement, their marvels, and the mysteries of the scientific world. When Michael Faraday began this series, it was with astronomy. We are going to show you many miracles of modern astronomy, but let me show you something which was shown here to members in 1855, one of the first ever photographs of the moon, the high technology of the age. At the time when the director here, John Tyndall, Faraday's successor, was discovering the existence of the greenhouse effect. Professor Malcolm Longair, as you will hear shortly, is a passionate Scot endowed with volcanic energy and zest and an immense amount of intellectual equipment. We are very happy this year again to present, in association with Shell, the Christmas lectures to you. This time, for the first time ever, we are organizing a competition which schools of Britain can enter, and more details will be given of that at the end of the program. It only remains for me again, boys and girls, young and old, to welcome you to the Royal Institution for the 161st series of our Christmas lectures. Enjoy yourselves.
In these 5 lectures, we're going to talk about the origin and evolution of everything there is in the universe. Planets, stars, galaxies, quasars, and the universe itself. What we're going to do is to use all the techniques of modern astronomy to try to build up the modern astrophysical picture of the universe. We're going to tell you what the problems are, and we're going to suggest answers to some of the deepest problems of modern astronomy and perhaps physics as well. So we've got a great deal to do. What we're going to do in this first lecture is that we're going to take a very grand view of the whole of the universe. We're going to give you the modern view of the universe, show the techniques that we use to study it, and then begin the definition of the problems that we have to solve. Now, whenever I give lectures like this, the first thing that people always say to me is, how can you imagine these enormous numbers and distances and sizes that you find in astronomy? You're all familiar with these numbers which have got one little number and then a magnificent string of zeros on the end. Well, the answer is very simple. I never bother about them at all. The simple way of understanding sizes, scales, and dimensions in the universe is always to think of one scale relative to the other. And what I'm going to try to persuade you is really the universe is a pretty cozy place. In fact, it's not really all that vast. And I feel very much at home in this rather cozy universe of us. So let's begin this way to show how we shrink sizes in the universe. On the bench here, I've got a simple model of the solar system with a schematic sun here, and then the planets, Mercury, Venus, Earth, Mars, Jupiter, and Saturn at this end of the bench. Now, the only thing which is correct about this particular model is the relative distances from one planet or object to another. What I'm going to ask you to concentrate upon is the planet Saturn. Here is a beautiful image of Saturn, and this is a very important recent image. It was taken by the Hubble Space Telescope only within the last few months and shows wonderful detail of the activity on the surface. Now, the reason I choose Saturn is simply to give you a scale of distance. So if I take the distance from the Sun to the Earth, then the distance from the Sun to Saturn over here is only a factor of 10. So although the distance in kilometers might be an absolutely enormous number, if you think of it simply as being 10 times the distance from the Sun to the Earth, then it's really quite a small number. And that's the beginning of our hierarchy of distances going up in the universe. Now, the big problem about models like this is that we can never get everything right to scale. For example, if we were going to make Saturn the same size relative to the Earth, we would have something which looks rather like this. Well, all it proves is you can't have everything. You can't squash everything into one lecture theatre. Now, that gives us a sort of dimension for the solar system. The next question is, how far have we got to go to get to the nearest stars? Well, again, it's quite a small number. You've only got to go 20,000 times the distance from the Sun to Saturn to get to the nearest stars. Now, my colleagues here at the Royal Institution, Dr. Bryson Gore, Pippin, and Jonathan have put together a really magnificent model of the 60 nearest stars to the Earth. And I'm going to get an opportunity today, one of the few opportunities one will ever get, to wander among the stars. Here are the 60 nearest stars to the Earth. They're all within a distance of about 17 light years. Now, you remember, a light year is the distance that light can travel in 1 year. So this is really very nearby indeed. Here is our Sun, here in the center of the distribution of stars. And the nearest star to us is this system here called Alpha Centauri. And this is only a distance of 4.3 light years from our own solar system. That's only 20,000 times the distance to Saturn. Now, this magnificent model has got lots of other wonderful features about it. It shows the correct colors of the 60 nearest stars. So we see, for example, rather bluish-white, large, massive stars. These are rather hot blue stars. We see stars like the Sun, and we see rather cool, small, red stars in our vicinity. The blue stars are the large stars, the massive stars, and the red are the small and cool ones. We've got to explain why that is later in this lecture. In addition, there are one or two oddballs. There are these funny little stars that we see here, these little blue stars, which are terribly tiny, but are very hot. These are the things called white dwarfs, and if you've got very sharp eyes, you will find 6 of them within this local distribution of stars here. You will also notice that not all of the stars are single. There are double stars, even some triple stars like this. Now, what about the masses of these stars? Well, they're all remarkably close to the mass of the Sun. Some of them are about 2 or 3 times the mass of the Sun. These ones here are only about 1/10 of the mass of the Sun. But it's quite a narrow range of masses. So this is our local neighborhood. And again, it is not such a big factor bigger than our own solar system. Here we see some of the slightly more distant stars, and these are very, very luminous stars indeed, and we've got to go to much larger distances to observe these Pleiades stars. Now, suppose we go up another factor in distance. Suppose we go up a factor now of 30,000 in scale from the distance between the stars. What do we see? We see a totally different picture of the universe. We see this enormous collection of stars here, which we call our galaxy. On this scale here, our own volume of space will be a tiny little bit, perhaps in one of these star arms out here. This model of our own galaxy contains, in principle, about 100 billion stars. That's 100,000 million stars, and they're all held together in this beautiful spiral pattern by the gravitational attraction between the stars. Probably our own galaxies looks something like the Andromeda Nebula that we see here on this screen. Here we see a central bulge in the galaxy. It's a disk-like galaxy, and we will be sitting rather far out on the edge here of the distribution of stars. Now, you can immediately appreciate a big problem, and that is that if we're sitting out here and trying to see what our galaxy looks like, we're sitting inside the disk, and so we don't get a terribly clear view of the universe. Now, it'll be very useful at this point to talk about the way in which we can actually convert the sky that we observe above us into something which we can plot on a two-dimensional sheet of paper. So I'm going to ask Bryson to pass me a model of the whole sky. Thank you, Bryson. Good. Right. Now, here we have got a model of the whole sky. It's the whole sky, northern and southern hemisphere, has been plotted on this map here. Now, I need assistance here. Would you like to come and help me? Just you come forward to help me? What are your names? Gillian? Tom. Good, right. Now, Tom, you've got to hold this map of the sky. I need you on this side to help to hold it, because we've got to do some interesting things with this. Now, you will notice here, this is the whole of the sky on the surface of this globe. And you will recognize some familiar things. Now, if we rotate it around this axis this way, that's right, you will be able to see here the plough and the stars here pointing up towards the North Pole. If we rotate it round a bit further this way, let's go around that way, you'll see down at the bottom we should have the Orion constellation here. So this has just got the whole of the stars in the sky onto this one picture. Now, running across this picture, we've got this band of the Milky Way. Now, the Milky Way is our own galaxy, but seen from the inside. And so what I'm going to introduce you to is how to convert this globe into a picture of the sky in what we call galactic coordinates. Now, the first thing we've got to do is to rotate the globe this way so that we get that's lovely, we get the Milky Way running right along the equator of the globe now. And now we've got to find the center of our galaxy, which is this little red spot here. So perhaps you can now rotate this whole sphere around this way so that the red spot points there at the audience. Is it going there? Got it? That's super. And now we've got the way in which we can plot our maps of the sky. What we do is to now unwrap the whole of the sky and plot it on a two-dimensional piece of paper. Thank you very much. That's terrific. Good. And this is what we end up with. You see here what we've got. We've got the Milky Way running across the center of our diagram. We've got the center of our galaxy in the middle. Here we're looking out through vertically upwards through the galaxy. Here we're looking vertically downwards out of the galaxy. Now, I spent a lot of time explaining that because we're going to look at lots of different maps of the sky in exactly this particular projection. It's what we call a galactic a picture in galactic coordinates with the Milky Way and our own galaxy running right across the center. Now, having started talking about galaxies, let's make one or two important statements about them. Galaxies are really the building blocks of the universe. They're the objects which define the very large-scale structure of the universe indeed, and I thought we ought to have a look at some of them so that we can understand the things which we have to explain. Here is another beautiful spiral galaxy here with a rather bright central regions and wonderful spiral arms going around the outside. Many galaxies in the universe are like this. There are also elliptical galaxies, which are shown on the next image. They don't have disks, but they're much more spherical or spheroidal distributions of stars, which just are held together by their own self-gravitation. Every now and then, we find unfortunate things happening to galaxies. Here on the next slide is an image of galaxies in collision. This is clearly a rather unfortunate accident that's happened here, and all sorts of terrible things are going to happen to both of these galaxies. We're going to show you in the fourth lecture exactly what comes out of these collisions. Sometimes we find collisions like this one on the next slide, which really is a horrible accident. We've got this ring galaxy with all the stars out in a ring. This is a horribly unstable sort of looking galaxy, and almost certainly one of these galaxies has taken a pop shot through the middle of that galaxy and caused tidal waves to go out through it. But these are the sorts of things that can happen in the universe of galaxies. These systems are all normal galaxies in the sense that they consist of gas and stars. But there are other sorts of galaxies which are very important indeed for our story and which will provide some of the most difficult and challenging problems we'll try to solve. Now, this galaxy here looks a fairly common or garden sort of galaxy. It's got a central region here. It's got spiral arms. You can't really see them terribly clearly out here, but take my word for it, they are there. And it looks a pretty quiescent sort of system, except when we take a short exposure photograph of the same region of sky. Now, I'll ask you to concentrate upon this set of 3 stars here, because now when we look at the next slide, we see the short exposure. Here indeed are the 3 stars again, but look, a star has popped up in the middle of the galaxy. This should worry you, because this cannot be any sort of normal star at all. It would have to be round about 1 billion times or more luminous than our own sun if it was to appear as brightly in this galaxy. And this is one of the objects which we call active galactic nuclei, which is one of the main topics we will talk about in our 3rd lecture. Now, there are other galaxies like this one, which we see on the screen, which are even more extreme. And in this particular example, the case of the galaxy 3C273, the nucleus has far outshone the galaxy itself. In fact, the galaxy itself is probably something like this. This tiny little clump of grains of silver on this picture, that would be roughly the luminosity of the galaxy sitting under this active galactic nucleus. This is one of the objects we call quasars, quasi-stellar objects, which are the most powerful sources of energy we know of in the universe. They are round about 1,000 billion times more luminous than the sun or more, and all of that energy is coming from a tiny little region. We're going to have to use entirely new physics to explain these phenomena. Well, that's enough for galaxies. What happens when we go on up in scale in the universe? What do we come to next? Well, next we come to the clusters of galaxies. Now, here is a rather beautiful cluster of galaxies. You can see galaxies here, 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 here. You cannot only see some of the brightest ones in this picture, but in fact, there are many thousands of galaxies in this cluster. Now, our own galaxy would not be specially interesting on this picture. It would probably be something like this galaxy here. In other words, it wouldn't be anything like this giant monster here sitting in the middle of the cluster. We've got to explain how they came about, too. Now, in our scale of sizes in the universe, the size of this cluster here is around about 100 times the size of our own galaxy. So that gets us up yet to bigger scales in the universe. Now, what about when we go to even bigger scales? Well, this is entering one of the most important and exciting areas of modern cosmology, because the large-scale structure of the universe is one of the most difficult problems to explain according to our understanding of current astrophysics. Now, let's have a look at this next picture, which is showing the whole of our northern galactic hemisphere with all the stars taken off. In other words, remove all the stars from our own galaxy and leave only the distant galaxies behind. What we see here, looking in the center of the picture, is looking vertically out of the plane of our galaxy. And when we go round this circle round the edge of the picture, that is looking through the plane of the galaxy. So it's not surprising that we start to lose galaxies round the edge here. That is because of dust obscuring the galaxies in these regions. What it means is that we get an unobscured view of the universe in the central part of the diagram here. Now, the cluster of galaxies that we looked at last time is probably only one of these dots here. So this is a picture of the universe on an absolutely gigantic scale. So when we look in the unobscured central regions, what do we see? Well, you see, the universe looks far from regular. You can see there seem to be holes here. There seem to be some sort of filaments here, sheets of galaxies. And we really want to know whether or not these are real features of our universe. Now, to really establish that, we need to measure the distances of the galaxies as well as their positions on the sky. And that has now been done by Margaret Geller, John Hooker, and their colleagues at the Harvard-Smithsonian Astrophysical Observatory in a huge survey of almost 30,000 galaxies, in which they've measured the positions and the distances of nearby galaxies. It's a really mammoth undertaking. And that gives us a three-dimensional view of what the large-scale structure of the universe looks like. We've got a wonderful video here, which we've been sent by Margaret Geller to illustrate this point. Now, let me show you what's going on here. In the very center of the picture is our own galaxy, and then we go out with distance as we go along these radial coordinates in the sphere. Now, what happens in the video is that we start to rotate the whole of this picture so that you can see the three-dimensional structure of the universe. Well, let's start the video now. Here we go. We're just about to rotate the whole universe of galaxies. Now, you can see the distribution of galaxies certainly is not uniform. Look at all these long filaments, the big holes, sheets of galaxies. We can see some clusters. But that is our universe. It is by no means uniform. I will stop the picture here, and I will zoom in so you can get another three-dimensional view. You see this amazing cellular structure that is in the universe. The distribution of galaxies certainly is not uniform. There seem to be large holes in the distribution. There seem to be filaments of galaxies. Now, how can you then imagine this distribution of galaxies? Well, I've got a beautiful model here of our local universe. Richard Gott and his colleagues at Princeton University have done some wonderful studies of the structure of galaxy, the distribution of galaxies in the universe. And here is the ideal model for what our universe looks like. You recognize it's a sponge. Now, I don't know if you've ever thought about a sponge, but it really is a rather remarkable object. Because you will notice that the material of the sponge clearly is all held together, or else the thing would fall apart. But in addition, the holes are all joined together. And this is the wonderful thing about a sponge, that the holes are all joined together and the material of the sponge is all joined together. You could take a piece of string and put it going through the sponge, and you could pull it out the other end because there's holes running all the way through. If you want to convince yourself in your bath tonight, take a piece of string and put it through your sponge. But don't blame me if you get into trouble. So that is our model of the universe. We live in a spongy type structure where the galaxies are distributed in the material of the sponge, and there are these large holes which run continuously through the distribution of galaxies. Now, what are the size of these holes? Well, the size of the holes are round about 50 times or 100 times the size of a cluster of galaxies. So we're getting up yet again to even larger scales in the universe. We've only got one more step to go. What's the size of the universe? It's very simple. It's only about 50 times the size of the big holes. This may surprise you. And it all depends upon what I mean by the size of the universe. Now, this leads us to one of the most important concepts in astronomy and cosmology, and that is that light only travels at a finite speed from its source to the Earth. And therefore, when we observe distant objects, we're not looking at the universe as it is now, but as it was in the past. We know it takes light 8 minutes to travel from the sun to the Earth, and it will take correspondingly longer to come from distant parts of the universe. Now, what I mean by the size of the universe, then, is the distance that we can look to in the universe when we see it more or less as it is now. If we were to look any further away, we would not be seeing the universe as it is now, but when it was much younger than, say, half of its present age. Let me illustrate this on a space-time diagram here. Now, you're all going to become real cosmologists by the end of this course, and cosmologists love space-time diagrams. Now, what a space-time diagram is shown here. What we do is to plot time running up the diagram and distance running across it. We're going to show in lectures 4 and 5 that the universe started with a Big Bang. And I've shown that Big Bang starting here. And I've shown a galaxy moving away at constant velocity with respect to us in this direction. Now, we only observe objects in the past, and light comes to us at the velocity of light, along what we call our past light cone. So that we observe this galaxy in the expanding universe not at the present time, but when the light left it, which was at a much earlier time in the universe. Now, what I mean by the size of the universe, then, is the size of the universe when it was roughly its present age. Say, going from the time when the universe was half its present age to the present time, that's what I call the present size of the universe. And it's a very useful operational definition just when the universe was half its present size. Now, I think I want to, just to convince you that things evolve over that time scale, let me ask you a question. What's your name?
David.
David, right. How old are you, David?
15.
15. When you were half that age, you were only 7.5.
Yeah.
Were you different when you were 7.5 as compared with what you are now?
Yes.
By a lot?
Yes.
Good. The same happens to the universe. You see, over a factor of 2 in time, things change. David has evolved enormously over a factor of 2 in time. I've evolved by an enormous factor. I used to have hair a factor of 2 long ago at that stage. But it simply shows that we expect all systems to change significantly when they are half of their present age or younger. And that is what I mean by the current size of the universe. There's, of course, lots of stuff beyond that. But if we look at it, we either see it much earlier in the universe or else the light hasn't reached us yet. So, you see, that's why I call the universe such a cozy place. On the next overlay, I have summarized how we get to the edge of the universe in these 6 easy stages. We've got, just simply think in relative terms. We go from the Sun to Saturn, to the nearest stars, to the size of galaxies, to the size of clusters of galaxies, to the size of the large holes, and then right up to the size of the universe. To put it technically, just think logarithmically. Don't bother about all the nothings, just think of one size relative to another. Now, you may have noticed that Bryson and his colleagues have been assembling a whole pile of kit on the bench around me here, and you may have wondered, what on earth has this got to do with astronomy and cosmology? We've got here a television transmitting dish that works at radio wavelengths. We've got here an infrared burglar detector, which responds to the radiation of hot bodies. We've got an optical camcorder here, which responds to optical light. Here we've got a rather wonderful X-ray machine, a dentist's X-ray machine, which can take images of your teeth using X-rays. And here we've got a Geiger counter, which measures gamma radiation, the radiation which appears in natural radioactivity. Now, the reason for showing you all of these, what I would call everyday devices, things which you may have come across in your everyday life, is that they are all using what we call electromagnetic radiation, which is the same stuff as light, but with rather different wavelengths. Now, we've got to talk a good deal about waves at this point, and so let's do some experiments just to demonstrate the key properties of waves that we need to understand what is going on in the universe. I've got here this really rather magnificent wave machine, and I would like to invite some very brave person to come and help me. Would you like to come and help me? Yes, what's your name?
Katie.
Hi, Katie. Right. You've got to do some very important experiments. Now, we're going to do 2 experiments. You will do one of them, I will do the other. Okay? Now, we want to demonstrate some properties of waves with this wonderful wave machine. It's a machine which, when we wiggle the end here, then the perturbation, the slight motion, is then communicated to all the other ones as it waves along there. Right? So what I want you to do is to start by just sending a nice simple wave by raising this last one here up and down quite gently like that. Now, the number of times per second I waggle my hand up and down is the frequency of the wave. So you try and do that, and I'll explain what happens. So nice and gently, up high, higher. That's right, up we go. Just keep it going nicely. Now, you'll see we get these beautiful waves produced here, up and down, up and down. And you'll see there's a certain wavelength, which is the distance between the wave crests of the waves. So with a low-frequency wave, we've got rather long waves. Now, Katie, this is the difficult bit. Now you've got to do it as fast as you can, but keeping big amplitude here. Off you go. 1, 2, 3, 4, 5. Off you go. Now you see, at the high frequency, we get lots more waves along the bench. You can see that we've got around about 5 or 6 waves going along the bench. That's terrific. Well done. Thank you very much, Katie. That's terrific. Now that demonstrates for us a very important relationship between the frequency of waves and their wavelengths. And we've summarized that relationship on this picture here. The wavelength was the distance between the wave crests, and the frequency was the number of times the wave crests were passing this point. And what we find is that if we multiply the frequency of the waves by their wavelength, we get the velocity of the waves. And if these happen to be light waves, this would just be the speed of light. It was one of James Clerk Maxwell's wonderful discoveries. He was one of the past professors of physics here at the Royal Institution, that indeed electromagnetic waves move at the velocity of light. So that's the first thing, which Katie has helped to demonstrate. Now, the second thing we want to demonstrate is that the waves can actually transmit energy. And what we've done here is to arrange to have a little ball here in this tube at the end of the wave machine. And I'm going to pass some waves to show that they carry energy. Now, if you've been hit by a wave on the beach, then you know jolly well that waves carry energy. But let's just demonstrate that this actually happens here too. So I will start by sending down quite a low-frequency wave, one like that Katie just sent down first of all. So we'll send a rather low-frequency wave down the machine like this and see what happens to the ball at the end. You see that the ball is being knocked up in the air a little bit, and that means that we're transmitting energy from the wave to the ball in the tube at the end. That was quite a low-frequency wave. Now let's put a high-frequency wave down this. Now I've got to work very hard and make this machine go as fast as it can. But just watch what happens. Now, the same happens for electromagnetic waves. In these cases, when we look at the optical waveband, for example, the red light, it has got long wavelengths, and when you go to the blue end of the spectrum, it has got short wavelengths. But of course, there are many more waves outside the optical waveband, and that is what we have with these machines here. Here we've got radio waves, which are exactly the same as light, but of very long wavelength indeed. Here we've got the infrared detector, which has got rather shorter waves than the radio waves, but still much longer than optical. The optical waveband we've talked about. The X-rays are very high energy waves. They carry lots of energy and of short wavelength. And the gamma ray detector has got the highest energy and the shorter wavelengths. Now, the next key concept that we've got to deal with is the relationship between temperature and wavelengths. One of the most important things we have to understand about this part of astronomy is that when we observe things at a particular wavelength, we're also getting a picture of that object at a particular temperature. There's a close relationship between the wavelength and the temperature. And this was first discovered in the 19th century and is known technically as Wien's displacement law. But we're going to illustrate this by doing some experiments on stars which we make here on the bench. What we're going to do is to show you the spectrum of a star, which we're going to simulate by a cannonball, which we're going to heat up to a very high temperature. Now, Bryson has now heated this cannonball up to 1,000 degrees Kelvin, and you can see it's a fairly impressive object, and we're going to do exactly what Newton did when he did his experiments with light. What Newton did was to put a prism in front of the source of light, and that dispersed the light into its various colors. So what we're going to do now is to close up the slit so that we only get a narrow beam coming through the slit. And now Bryson is going to put the prism in the path of the beam. And there you can see beautifully what's happening. What we've done is to take the light and split it up into its various spectral components. What we're seeing here is that the light of the cannonball has got some red light, some yellow light, and some green light. And that, if we were to measure the intensity of these different wavelength components, we would measure the intensity spectrum of the source. It's a very beautiful demonstration indeed of a star. And I must confess, it does not look unlike our own sun. We're going to leave that cannonball there, and we'll come back to it later after it's cooled off a little to see if there is a difference in the spectrum of the source. Now, we're going to do some computer simulations of exactly this experiment. Now, on the screen, we should have now a spectrum, an illustration of the experiment that we've just looked at. Now, what we've done here is we've got a star of some sort here, and then we put a prism in front of it here, which splits the light up into a red component, a green component here, and a blue component here. And this shows the wavelength range, including ultraviolet, optical, and infrared radiation. I've put down here the wavelengths of the radiation in nanometers. Now, what I'm going to do is to invite someone to come and help me. Would you like to come and help me? What's your name?
I'm Tom.
Tom, right. Are you good at numbers?
Fairly.
Are you good at computers?
Yes.
Excellent, good. Right. Now, what we then do is that we invite you, I'll tell you what numbers to put in. You've got to put in some numbers on the keypad here. And once you've put in the numbers, then just press return, and I'll explain what's going on the screen. Now, first of all, we want to essentially replicate the experiment we did here. We'll make the temperature just a little bit hotter. Now, would you like to put in 3,000 and press return? Here we are. In this computer simulation, you see we've got the correct orangey color for the star, and here is the spectrum of the light emitted by the hot body. It's what we call black body radiation, and it's got an absolutely characteristic spectrum. Now, the reason that the star has got this orange color is that there's lots of red, a little bit of green, and almost no blue. Now, let's look at our own sun. Now, our own sun is at a temperature of 6,000 degrees, so pop in 6,000. There we go. Now, you can see by this computer simulation, we've got the right color for the sun. It's the sort of off-white, a sort of yellowy white. And here is the intensity spectrum. You see that there's lots of red still, but there's much more green, and now there's lots of blue. Let's go even hotter. Let's go up to, say, 10,000. Now you see what's happening. As we go hotter and hotter, the maximum of the spectrum is moving to shorter and shorter wavelengths, higher and higher frequencies. And you can see we've now got white stars because we've got almost equal mixtures of red, green, and blue light in the spectrum. Now let's hit it really hard. Let's put in 20,000. There you are. We've now got blue stars. And that is because now the maximum of the spectrum has been shifted right into the ultraviolet region of the spectrum, and there's lots more blue than there is green or red. And that is why blue stars are hot and cool stars are red. That's terrific. Thank you very much. Now let's come back to our cannonball and see if it's cooled down a bit. Let's have the lights down to see if we can see if there's any change in the spectrum. Now the cannonball will have cooled, and so we should now begin to see a difference in the spectrum as compared with before. And here we see there's a very faint red color going up here. We've lost the green, we've lost the yellow, and that is because it is cooling down and the maximum of the spectrum is shifting to the longer wavelengths. Thank you very much. Now I want to summarize this very important point on the next slide here, which shows the relationship between temperature and the wavelength of the light. And this is an absolutely enormous picture here. We've got the waves going from radio to infrared, optical, ultraviolet, X-ray, and gamma rays. And what we've got up this axis is the temperature going over really enormous ranges indeed. This line going across the diagram tells us the relationship between the temperature and the frequency at which we would expect the radiation to come out. So, for example, when we look at the optical picture of the sky, then we're basically looking at objects which are about 10,000 degrees Kelvin. And the reason that we see the sky with our optical eyes is simply because stars and gas clouds are all about 10,000 degrees Kelvin. Galaxies are simply the superposition of stars and gas clouds, all at a temperature of around about 10,000 degrees Kelvin, and that is why it looks so beautiful. There are very good astrophysical reasons why the stars should be at these temperatures. If we want to study the very hot universe, we've got to go to the X-ray wavelengths. Clearly, the temperatures must be about 10 million degrees here. To observe very high temperatures, about billions of degrees, you have to go to gamma rays. To look at the cold universe, you look in the infrared waveband. And if you're interested in the very, very cold, you go to the millimeter or to the radio waveband. Now, we want to illustrate how this different way of looking at the universe gives us completely different pictures of the various objects that we look at. The first example I'm going to show you is looking at our own Earth. Now, my colleagues at the meteorological office have very kindly provided me with pictures of the Earth observed in the infrared waveband, so that the regions which are hot will shine very brightly, those which are cold will be rather fainter. And here is a picture of the whole planet taken within the last month, and the color coding is such that this region is very hot and this region here is very cool. And there was rather a lot of cloud on this particular day, but you can see that the Sahara Desert here is very hot. You can see the Kalahari Desert down here, if it wasn't covered with cloud, would also be very hot. So this is just showing you if you select your wavelength correctly, then you can be temperature sensitive in the things you see. If you make a map at a longer wavelength and you subtract this map off, you will see where the cooler regions are. And on this next picture, we've done that. We've simply subtracted the temperature on the first map from that at a longer wavelength so that we bring up the cold regions which are in the northern and the southern latitudes. So when we choose a particular wavelength, then we get a different temperature picture of what we are looking at. Now, one of the great traditions of the Royal Institution is that there are lots of explosions. And I want to now give you one or two examples of explosions in astronomy, that we know that there are explosions of stars, explosions of quasars, and explosions in galaxies. So let me just remind you what a tiny little explosion is like. Let's have a little explosion, Bryson. Thank you, Bryson. Excellent explosion. Now, as I said, that was an extraordinarily tiny explosion, and we want to do a much bigger one now. What we want to do is to explode a whole star. Now, you may recall that there was great excitement in 1987 when a star exploded in the Magellanic Clouds. The Magellanic Clouds is the dwarf galaxy, which is our nearest neighbor in space, and here is the central region of that galaxy. This is what the galaxy looked like before the 24th of February in 1987. But then, on that night, suddenly, a star appeared. And this was the explosion of the supernova 1987A, which has been perhaps the most important explosion of any star ever, because we've been able to study it in detail with all modern technology. I'll show you on the next slide what has happened to this supernova. This is actually a picture taken by the Hubble Space Telescope within the last few months, showing the star here, which is now expanded so that you can resolve the size of the exploding star. But it has also lit up a beautiful ring of gas round about the supernova itself. So it's a beautiful example of what you can do with the Space Telescope to study the evolution of that supernova. Now, the next supernova I'm going to look at is rather old. It went off about 250 years ago, and nobody saw it. We don't quite know why. It may have been a long cloudy patch, or maybe people weren't looking, but nobody saw it. But we know it went off around about 250 years ago. Let's have a look at the optical picture of this exploding star, first of all. Now, this is the optical picture, and you would agree it isn't all that impressive. You'll see there's scraggly little bits of filaments here, other little bit of filaments up here, but it really isn't all that convincing. The star must have exploded round about here, and the only reason that we see these filaments is because they've cooled to temperatures at which we can see them in the optical waveband. However, if we make an X-ray image of the same field, here it is, you see that it's very intense indeed. It's very convincing that this was a almost spherical explosion, and this gas, to be observable at X-rays, must be at least at 10 million degrees. In other words, the gas has been heated up to an enormous temperature by the explosion of the star. And so we get a much more complete picture of this exploding star when we observe it not only in optical, but also in the X-ray waveband as well. In this example, we've gone from the optical waveband to hotter temperatures. Let's go from the optical waveband to cooler temperatures. The next object we'll look at is the Orion Nebula, and we're going to say an enormous amount about the Orion Nebula in the next lecture. But this is just a beautiful optical picture taken by David Milne at the Anglo-Australian Telescope. And you can see the beautiful filamentary structure, all of which is being excited by 4 stars in the center of this nebula. Now let's go to a longer wavelength, to a wavelength of around about 4 times longer, so that we can look at it, the cooler material. This is the same object, but now you see it looks completely different. All the wispiness has gone away. The 4 stars are still there, but look at all the other stars that have appeared, as well as all of this red, cool stuff which is emitting in the infrared waveband. That material is going to be very important in the discussion in the next lecture, because we believe inside these clouds, that's where the stars are being born. Now, I want now to look at the whole of the sky again, but we're now going to look at it in all the different ways in which we can now do modern astronomy, and we're going to bring on the instruments that we need to do them. We're going to uncover yet more problems that we've got to understand in the subsequent lectures. We're going to start, first of all, back with the optical waveband, and here's a rather beautiful Cooke telescope, which is the property of the Royal Institution. We go back to this picture you've seen before. I remind you, the Milky Way is stretched along the center of the diagram, looking out of the plane of the galaxies at the top, and looking down out of the plane of the galaxy is at the bottom. Now, as I've said already, when you make optical observations, you're looking at the universe at temperatures of around about 3,000 to 10,000 degrees. And that is what we're seeing in this particular picture here. We're seeing stars and gas at that temperature. Now, suppose that we go to a somewhat higher temperature. We've got here a telescope which is designed for making observations in the X-ray waveband. Now, you're used to seeing photographic plates for taking optical pictures, and you may even know about CCD detectors which are inside the television cameras which are taking pictures of me just now. In the X-ray waveband, we have a slightly different type of detector here. It's what's called a microchannel plate, in which there are lots of little tubes in this little disk here, in which the X-ray signal is amplified and then put onto a detector like this, which stores the charge which is produced by the microchannel plate. This particular detector here was built at the University of Leicester and has been incorporated into this wonderful X-ray satellite which is flying above us just now. This is the ROSAT satellite, which has been in orbit for several months. It is working magnificently and is producing a wonderful map of the whole sky. It is a collaboration between Great Britain, Germany, and the United States. I do not yet have a map of the sky to show you taken with this telescope, but here on the next slide is a picture of the X-ray sky taken by an earlier satellite. You will see here where the positions of all the strong X-ray emitters are. You will see that we can still just see the plane of the galaxy here, outlined by a slight concentration of these bright X-ray stars towards the plane of the galaxy. But in addition, there are lots and lots of these sources away from the plane. All of these objects have got to be extremely hot if they're going to emit X-rays, and it turns out that there are various ways in which this can happen. Either you have exploding stars, such as the supernova that we looked at before, or else these may be binary sources in which matter is falling onto extremely compact stars. we're going to have a great deal to say about these very compact stars in the third lecture. But in addition, away from our own galaxy, there's this large population of objects out of the plane. And these are all very, very distant galaxies indeed. They are very powerful sources of X-rays, and they're almost all associated with the active galactic nuclei of the same type that we showed earlier, the things in NGC 4151 and in 3C273. Again, we've got to explain where this intense X-ray emission comes from. If we go to even higher energies, then we go to the gamma ray energies, and then the telescopes start to look even more peculiar. What I've got here is a gamma ray telescope which was built at the University of Southampton and which was flown on a balloon. And it doesn't really look like a telescope at all. But what happens is that the very rare gamma rays come in through the top of the instrument, and then there are lots of layers of heavy materials like tungsten and lead in order to stop the energetic gamma rays. These then give a signal which can be detected by the electronic detectors. A detector exactly like this one was flown in the COS-B satellite of the European Space Agency, and here is a model of that satellite. This satellite contained one of these large detectors, and through its lifetime of about 8 years, it managed to detect round about a few thousand gamma rays. So the rate of arrival of the gamma rays was very, very low indeed, but it did produce this magnificent map of the galaxy. Now, I'm afraid they only managed to cover the galactic plane because the gamma rays came in at such a low rate. But again, you can see that the plane of our galaxy is an intense emitter of gamma radiation as well. Now, since these are gamma rays, it means that there must be an extraordinarily high temperature gas present in the plane of our galaxy. In fact, its temperature must be billions and billions of degrees. In fact, we know that this is what we call a cosmic ray or a relativistic gas, where the particles are of extremely high energy, far higher than the energies we're used to on Earth. And we've got to explain where all these high energy particles came from. They are not the normal stuff of stars or gas in our galaxy. We've gone to the high energies. Now let's go to the low energies. When we go to the wavelengths which are longer than the optical waveband, then we're starting to look at cool regions in the universe. I've got here the type of detector which we use in infrared astronomy. This is an old detector which was built at the Royal Observatory in Edinburgh. In order to be able to observe the sky at these long wavelengths, at which the sky will be very bright because of its thermal emission, we've got to cool our detector to a very low temperature. And you will see inside here cans for containing liquid nitrogen and liquid helium in order to cool the very small detector element that we have here down to such a low temperature that it can actually see the sky and not be completely swamped by background radiation. Nowadays, we have wonderful arrays in infrared astronomy to make pictures of the sky, and one of the most exciting new projects in astronomy will be the European Space Agency's Infrared Space Observatory, of which we've got a magnificent model here. This is a telescope designed to observe the sky in long infrared wavelengths. And most of this volume here is nothing but liquid helium, liquid hydrogen, in order to cool the whole of the telescope down to a low temperature. All of these shields here are to prevent too much stray radiation getting into the telescope. Well, this will be an absolutely wonderful instrument for studying the whole of the sky in infrared wavelengths, which we cannot observe from the surface of the Earth. What we see in the infrared waveband is shown on this slide here. This is the map of the sky taken with the IRAS satellite, which flew around about 1980 to 1981. And this is now working at a wavelength of around about 60 to 100 microns, very much longer than optical wavelengths. And you see again the galaxy is very bright. But now it is very bright in cold material. This material in this picture is all at a temperature of around about 60 to 100 degrees Kelvin. In other words, it's very, very much cooler than normal material that we're used to on Earth. On the other hand, it had to be heated somehow, and that is one of the key things that we will learn about in the next lecture. This radiation is all associated with the radiation of young stars, possibly even protostars, and dying stars, heating up dust in the space between the stars. If we go even cooler, we come to the millimeter wave band, and then again the technology changes again. Here are some examples of millimeter technology. This little horn here was made at the Mallard Radio Astronomy Observatory in Cambridge, and is the type of little horn for detecting millimeter waves. Everything is micro-miniaturized. Here is a little amplifier which goes with that millimeter receiver. Now, on the next picture, I show you a quite amazing map of the sky made only this year by a satellite called COBE, the Cosmic Background Explorer. And now this picture is completely different. You can see that we can just see the plane of the galaxy and no more. You can see it there. But the picture is completely overwhelmed by the hot radiation here and the cool radiation here in regions which seem to be unrelated to our galaxy itself. What is happening is that this is not the total radiation at all. This is only the deviations of the temperature away from a completely uniform sky at a temperature of 2.736 degrees Kelvin, only about 2.5 degrees above absolute zero. This radiation here is the famous microwave background radiation, which is the remnant of the hot Big Bang. This is the radiation which was filling the universe in the early stages, and this is its cold remnant. COBE has made magnificent observations of the spectrum, and since we've talked about these black body spectra, I must show you the spectrum. An absolutely magnificent result. On the next slide, this is the spectrum of that background radiation, and you can see it is as perfect a black body spectrum as you will find anywhere in nature. This is the cool remnants of the very hot early stages of the universe, and we will talk a great deal about it next time. To finish our story, we go to the radio wavelengths, and then the detectors change again. Here is a parametric amplifier, which is used typically on telescopes like the Jodrell Bank telescope here. And here is the map of the sky that we obtain, a beautiful picture made by the astronomers at the Max Planck Institute for Radio Astronomy at Bonn. Again, you see the plane of our galaxy, but now look at all the stuff sprouting and bursting out of the plane of the galaxy. This ought to be very cold, but it isn't. It's actually extremely hot radiation, now the radiation of very high-energy electrons. These are more high-energy particles that somehow have been created in our universe. In the third lecture, we've got to explain where these particles came from. So what we've done in this lecture has been to run through the whole of our universe, and I want you to remember just one or two key things. First of all, remember the universe is not all that large. We can get up to the edge of it in 6 easy stages. Remember the sponge, which tells us about the large-scale distribution of galaxies. Remember, we must not be chauvinist about wavebands. All wavebands tell us something central for understanding how our universe works. What we have to do over the next 4 lectures is to put all of this together to understand in a coherent way how it is that stars were born and evolved, how galaxies, quasars, and the universe evolved. Our story next time in the next lecture will take up the origin of stars and how they work. Thank you very much.